Today I'll talk about scaling neural networks. I'll actually go into three major areas. First, why it's important, and second, the infrastructure you need to make it work, and third, any considerations you need for like model development and training. So why does scaling matter? The first reason you should think about scaling is mostly because of rapid iteration. So a lot of you who have actually been working in machine learning before know that like your training almost never works the first time. You have to change hyperparameters. You have to like test out different model structures. So rapid iteration is quite important. And specifically, like if you want to test out an idea, it's much better if you can get results back in minutes or hours or even like one day than if you have to test your model to convergence in like 2 weeks for a lot of image models to see if it works. So this actually, especially if you have a larger organization and you have a lot of people testing out all different kinds of models, like this kind of time for development can actually hinder their productivity. If you're just like a software engineer, and you can think of it as analogous to build time. So if compilation takes 30 minutes, then you basically have to context switch and work on something else before you can continue. So another thing that Google actually recently published about was the effectiveness of larger data sets. And scaling actually makes larger data sets work better. So if you actually think about Imagenet, it's a 1 million image size data set that really hasn't changed like since it was published in about 2012. During that time, GPU power has actually grown quite a bit. Model size in terms of number of layers, and in some cases number of parameters, has actually grown substantially since then too. And people have been doing this, scaling up to making larger models work to improve the classification or object detection accuracy. So what we found is that as you grow your data set size, the model quality essentially grows log linearly. And so actually training on this amount of data and improving your model to that extent just requires essentially more hardware. Another thing that this group found was that to take advantage of larger data sets, you actually needed larger models. So for example, ResNet 50, which is like a 50-layer residual neural network, does worse than a larger model that has like 150 or more layers. And a topic that is a favorite of mine, and actually I think will be very impactful in the future for neural networks, is automated machine learning. So Jeff has talked about this quite a bit, but I'll go over this again. So the current way that people do training right now actually requires a lot of machine learning expertise in both model development and actually just getting the model to train to convergence. So if you have worked with neural nets before, you can kind of understand that neural nets are pretty finicky. They're very sensitive to like learning rates and other types of hyperparameters. And this takes a long time. So kind of the future that we think will happen is that you can just supply your data and tons of computation, and then everything will end up working for you. So our team has been doing research into this area, and specifically we've been doing both evolutionary and reinforcement learning-based architecture search. And these have actually produced state-of-the-art results in the domains in which they've been tested. So this actually appeared earlier this year in iClear 2017. Basically, reinforcement learning, you basically supplied some sort of reward signal. In this case, the reward was validation accuracy of the model after a certain number of training steps. So the recurrent neural network that was used here actually generates models sequentially, like each layer sequentially, trains them for a few hours, not to full convergence, and then it uses that reward to essentially learn what types of models work well. And this was actually one of the models it developed. So you can tell by its complexity that probably no person would have thought of to create this particular kind of model, although dense nets are somewhat similar in structure. And at the time, it was, I believe, the state-of-the-art or next to the state-of-the-art. And there are also other applications to this. So it also did search for recurrent neural network cells. So if you look at this particular cell, that it generated and contrast it with the long short-term memory cell, it's actually quite a bit more complex. And you might think just by looking at this that it kind of overfitted and created a cell that was only applicable to this particular task, but when tested against other tasks, it actually also worked better. So at the time, again, this was state of the art, but I believe somebody has improved upon this since then. And more recently, this is just from last month, neural architecture search. So there's often this trade-off. So you have essentially the amount of computation that your model requires for both training and inference, which is shown on the x-axis, and then the accuracy it gets on a particular task, in this case, Imagenet. So generally speaking, again, as you look at this graph, it does look somewhat log linear. As you increase the number of multiply adds, then the accuracy goes up log linearly. So you essentially want to get the best accuracy that you can for the minimum number of multiply adds. And the neural architecture search did it pretty much in every single case that you look at here. And specifically, the ones to the left are the kinds of models that you would want to deploy on mobile devices. And then for servers, you often have some sort of strict latency requirement. So you'd want to choose some sort of trade-off between the amount of multiply adds that are tolerable for latency purposes. But here, you can see that it actually did better than any other model in this particular task using fewer operations. Another thing that has involved a lot of research over the past many years are different optimization algorithms. And possibly the two most successful right now are Momentum and Atom. But these have been sort of hand-tuned, and a lot of theory has been developed behind the ideas here. So using neural optimizer search, using basically the same ideas. So in this case, you basically need to specify some set of primitives for your search space. So you might say take the square of the gradient term as one example, or e to the power of something as another example of some primitive you might supply. And then it'll create optimizers for you. So again, if you look at prior to this work, Momentum was doing this the best on this particular task. Atom in general is considered very good for many tasks, but so it generated a lot of different types of optimizers that are all quite plausible. So if you look at the best performance, it actually quite significantly improves upon Momentum. And another question you might ask is are these optimizers applicable to more general tasks, or are they just fitted to this particular task of image classification? And so they took this one of the optimizers on this list, one of them that seemed actually pretty plausible, and tested it on neural machine translation. So translation, the models there are completely different than image classification. And as you can see, it did better than Atom, which is considered often the state-of-the-art optimizer for many tasks. So these kinds of things actually just aren't possible without huge amounts of scale. And you can actually essentially build better models than those that exist right now just by searching for them. Another thing I'll mention that matters for scale is it actually enables you to solve different kinds of problems that you might not otherwise be able to do. So neural machine translation is actually one example of this. And the way that we actually train this model right now, we're not able to train over the full data set that we have. I believe Jeff mentioned that we actually only train over 1/6 of the full data set, and just more computational power would essentially improve upon these results. And AlphaGo does a form of Monte Carlo tree search at inference time, which relies on tons of computation, and during training time, it essentially trains against itself. So a lot of these new applications require as much compute as you can give them. And if you think about it, neural networks as they contrast to other machine learning approaches. So a lot of you may be applying boosted trees or support vector machines. Neural networks actually tend to only work better than these tasks when you have more data and more compute. So there's some threshold at which they cross, but neural networks just tend to improve the more data and more compute that you give it. And kind of going back to this as a reminder, like just the more data you have, the better you do. So I'll go into the infrastructure that you need to make scaling work. And in particular, I'll talk about all the topics you need to do to implement distributed training in your organization. So for those of you not familiar with distributed neural network training, there's actually a first decision you have to make. And often it's like simplest to make a single template in your organization such that people basically do the same type of training. And it has certain trade-offs. So the original TensorFlow and disbelief system, actually, the papers talked primarily about asynchronous training. And in asynchronous training, there are model replicas that each operate independently. And they they compute gradients and then update them in the parameter server, essentially independently. And this contrasts with synchronous training, in which each worker computes a gradient and then does a form of all reduce. And here I just showed ring reduce that basically sums up and actually takes the average of all the gradients and then applies them locally on each machine. And sort of as a best practice, generally at Google for the longest time, asynchronous training was actually somewhat more common. Sort of as a best practice, like generally outside, I would recommend starting with synchronous training because it is easier to get working. So both of these actually, when training, have the problem of stale gradients. So in asynchronous training, like when it pulls the weights from the parameter servers, there's some amount of time that happens before it finishes its gradient computation, in which case like the weights that it pulled from the parameter server to compute the gradient are actually pretty stale. So this happens for asynchronous training, but actually synchronous training is also like a form of like stale gradients because each worker is operating independently. If you think of like them applying the gradients in sequence, like essentially after each application, the gradient gets more and more stale. So this actually affects models when scaling. And I'll talk about that a little bit later when I go into model development and whether this works at all and in what cases it doesn't work. So for communication, TensorFlow actually supports gRPC, MPI, and InfiniBand. And these have all been contributed by different companies. The default mode for TensorFlow is gRPC, but for various reasons, like if you want to do RDMA, you may want to switch modes. And the way it works in TensorFlow is this communication layer essentially is used for sending and receiving tensors. So Yahoo and Minds.ai contributed different implementations for actually doing this send and receive of different tensors. More recently, Baidu contributed this MPI implementation that has an all-reduced primitive, like the one I showed before for synchronous training. Whether this makes sense for you really depends on the type of hardware that you have in your setup. The gRPC is sort of the default for a good reason because it's easy to get working and it doesn't require as much to think about. But if you have like strict performance requirements, then you should consider using one of these. Cluster managers. So a lot of you might be using different cloud platforms, running VMs. I would want to mention that everybody's running. I've talked with a lot of companies. Everybody basically has a completely different setup. I'll go into the benefits of cluster managers. So a lot of people do applications on hosts and do like configuration through Puppet, which is sort of stateful and like hard to maintain. If you deploy containers, then basically they're like pristine copies of like a certain state, ideal state, and it's much easier to like get things working. And for distributed TensorFlow in particular, when you want to distribute like a Python program pinned to a particular version of TensorFlow, pinned to like other dependencies, it makes deployment and work a lot easier if you run a cluster manager. And I think Google has something called a Google Container Engine that runs a Kubernetes instance for you. There are other cluster managers that you can use. I believe Amazon is also doing something similar for Kubernetes. And Kubernetes in general is a good choice here. And as of recently, so neural network training on GPUs tends to speed up things quite a bit. And as of recently, Kubernetes added support for requesting GPU resources. So what this means is that if you have a host with like 8 GPUs, then you can actually consider it to be a shared resource that multiple people are using at the same time. And they just need to request like a certain number of GPUs to make it work. So in the Google Brain team, I actually work primarily on TPUs. So I'll cover the impact like upcoming hardware will have on scaling. So this is what a tensor processing unit actually looks like. This is Google's hardware that is specifically designed for neural network training. It has, Jeff recently announced this, I believe, at Hot Chips, but so we've released some numbers here. We have 180 teraflops of computation, 64 gigabytes of HBM, and 2.4 terabytes of memory bandwidth on just this one board. These are designed to be connected together in larger configurations. So if you recall the synchronous distributed training that I mentioned before, this is specifically applicable to the configuration where these are deployed in huge amounts. And if you actually look at the internals, they basically have a scalar unit that can work with 32-bit floats and a matrix unit, which also can do 32-bit floats, but with accumulation in reduced precision. And this is what a TPU pod actually looks like. So if you want to like, the type of model development that I was talking about earlier, where you can train a model in like minutes to hours, if you can reserve one of these for a while, you can get models to convergence actually pretty quickly. And the interfaces that we're making for these actually, if you're familiar with TensorFlow, we actually are building something on top of the estimator interface. And it will soon be available in Google Cloud. And if you're a researcher, we're actually giving these away for free. So if you're committed to like open machine learning research, so visit this link at g.co/TPU signup if you want to be a part of that. More generally, there's actually a bunch of hardware that TensorFlow currently supports. So this is just a sample of some of them actually. And there are a bunch of hardware vendors actually besides NVIDIA who are developing other neural network chips. So how does this all work? In TensorFlow, we have something called a linear algebra compiler. So if you know TensorFlow, TensorFlow has this concept of a data flow graph where each node is an operation, and then each edge is a tensor to send to another operation. And you can actually take subgraphs of the TensorFlow graph and compile them down to assembly instructions. So the instruction set would depend on the type of hardware that you have, but essentially you can build different backends. So XLA has an interface where you basically specify how certain things should be compiled down into the hardware, and it'll work for different backends. Model development. Model structure is actually important, but I won't go too much into it because it's not an area of expertise of mine. But certain models are actually much easier to train than others. In particular, a common thing that people are doing now are training ResNets, which have residual connections, which basically add the features or concatenate the features of lower layers. And this kind of thing actually makes models train much faster than you would otherwise be able to do. So if just by possibly changing your model structure, you actually might reduce training time significantly. There's sort of two forms of parallelism when doing training in TensorFlow or with any other framework: data parallelism and model parallelism. And these aren't actually opposing things. You can actually kind of mix and match and combine them. When people think about training neural networks, they actually are more commonly thinking of data parallelism. And back to this picture, this was an example of data parallelism, both asynchronous training and synchronous training. Data parallelism is when you essentially have a complete copy of your model on different workers. So each worker, in some senses, is operating independently. And in async mode, they're actually operating completely independently. In synchronous mode, they're operating independently up until a synchronization point. So basically, like the way synchronous, which is the mode that I would recommend to people, works is each worker does the same kind of loop. It'll read the data, do a forward pass to the neural network, it'll do a backward pass to compute a local version of its gradient, and then notably, it'll average the gradients across workers. So here, averaging versus sum actually matters for hyperparameter tuning, depending on the type of loss you're using. This is what's referred to as an all-reduce operation if you're familiar with MPI or other, like NVIDIA's nickel. And then after you do this averaging operation, then you apply the average gradient to a local copy across all of your variables. So the way synchronous training actually works in TensorFlow is TensorFlow basically is agnostic to like the type of like structure your workers have. All it understands is like what devices you have. So you could have devices, you could have 8 GPUs all on one machine, or you could have 8 GPUs like across 8 different machines. And TensorFlow would actually look as just 8 different devices both ways. And the type of thing that you would do here is basically replicate the graph across the 8 different devices, and then do this all-reduce operation, and it would essentially be the same. So talked a little bit about this, but actually for the longest time, up until actually just like the past few months, it was actually unclear whether data parallelism could actually work for large batches. And for the most part, people actually never thought that it did work. So what would happen is if you like took the TPU pod that I showed earlier and then just tried training an image model on it using synchronous gradient descent, it actually would just not converge. And if you look at the date here, in iClear 2017, there was this paper called On Large Batch Training for Deep Learning, the Generalization Gap and Sharp Minima. People kind of talked about this generalization gap where if you ever try to do large batch distributed training, then your model quality would essentially be worse than if you had not done it. And so people were building like all kinds of new hardware to like assuming that data parallelism worked, but we actually were not sure that it did. Up until a few months ago, there were these 2 papers. One of them, the first one was out of Facebook, where it was entitled Training Imagenet in 1 hour. Essentially, they found out like different techniques and heuristics you could do for training like with very large batches. In particular, they mentioned you have to do like gradual learning rate warm-up and scale the learning rate linearly with batch size. But even in their paper, they actually found that their techniques only worked up until like 8,000 images at once. So if you were training on like much larger setups, then you could easily get to like 64,000 or larger. There's actually a recent paper from, I believe this was like less than a month old, from NVIDIA, where they showed that you could actually train on like even larger batches than that paper by, in their paper, they actually introduced a new form of optimizer where it scales the gradients based on the L2 norm of the weights and the L2 norm of the gradients. So there's a lot of stuff that, a lot of research that's still happening here, and we're still kind of figuring out the best practices to make this all work. This kind of stuff doesn't matter as much if you just have like a single machine with 8 GPUs, but it pretty much matters anytime you extend beyond that. So model parallelism is actually much less common, but it's actually important for a lot of specific tasks. So what I have pictured here is actually the neural network that Google uses for translation. And as you can see, it actually divides the model itself among 8 different GPUs. So why does model parallelism matter? For like larger models that actually don't fit on one device, so keep in mind these GPUs have somewhere between like 8 to 16 gigabytes of memory. For larger models that actually don't fit on one device, you typically want to split them up across many different devices. So that was one example of like a model parallel model parallelism in production. And sort of more generally, people kind of like hand tune these. So people do specific like device assignment for different subgraphs of your model. But getting good performance out of these is really non-trivial. And there's actually, like, if you look at this one, if you were just to look at this, the most obvious placement, if you had like 4 GPUs, would be to do something like this. And to do anything else would be like really complex to maintain and just difficult to work with. So again, reinforcement learning. So I mentioned earlier in the talk reinforcement learning for actually building model structures. Here you can actually do reinforcement learning for placing different parts of the model on different devices. And this was another paper by the Google Brain team. And we're thinking about, this is actually available in the TensorFlow code base, but we're also thinking about different applications that this might work with. And here, the reward signal is actually the amount of time it takes to do one step. And to actually understand the complexity of these kinds of placements, each color here is actually a different device. So these kinds of placements, if you were to do them by hand, essentially would be incomprehensible, unmaintainable. But if you just have a computer place them through reinforcement learning, then you can just remember the placement and it'll work forever. And for the models that were tested, which are common image and neural machine translation models, these were, again, better than expert humans at this particular task. Yeah, so as a reminder, model parallelism mostly matters if you want to fit very large models, which is like not that common unless you typically have like very, very large data sets. So reduced precision is actually a major trend that's happening now, and kind of stems from the fact that with neural networks, approximate answers are actually OK. So here, if you multiply 1.2 with 0.6, then getting some number that's approximately correct actually won't reduce the quality of your model for the most part. And also, for neural nets are essentially like huge numbers of matrix multiplies. So if you combine these facts, you can actually reduce the precision of anything that you need for training. So one common example of this is switching from 32-bit floating point to 16-bit floating point for both training and inference. And for a lot of models, this actually has no effect on model quality. Going down further from 16 bits to something lower kind of does, depending on the situation. But people are doing research on even like 1 bit. So as sort of a best practice, often the reason people do reduced precision is to fit on smaller devices. So a very common thing to do is if you need to deploy on a mobile device, you actually reduce your precision down to what's called like quantized 8-bit. So essentially, it's like an 8-bit integer where each number represents a particular range. And but for training, you typically can get 2x faster just by switching a 16-bit. For like very low bit ranges, like quantized 8-bit, you do need to initially train in 32-bit and then fine-tune your training in 8-bit to recover some of the lost accuracy that you do from going down to 8-bit. So as far as hardware support goes, a lot of you are probably running on GPUs. So most NVIDIA chips, particularly the data center level ones like P100 and their upcoming B100, actually support the IEEE floating point 16-bit format. And notably, they do 32-bit accumulation to recover some of the lost precision there. On mobile devices, mobile devices typically support both like 32-bit and 8-bit quantized. The first generation of TPUs that we had at Google actually only supported 8-bit quantized inference. And the TPU device that I've been spending time on primarily supports 32-bit floating point. So as a refresher for the training part of training distributed neural nets, So there are common optimizers that I mentioned in the past, and specifically, as a refresher, the most common ones are probably momentum and atom. And these two papers I mentioned before for making distributed, like large batch training work, specifically on images, actually have certain best practices, and we've sort of tested these out and basically agree with them. You do need to do like gradual learning rate warm-up, so you can't just fix like normal neural network training where you just have a fixed learning rate that you decay over time. You actually need to warm up your learning rate for a number of epochs. And in their paper, you need to scale up learning rate with the effective batch size. So the more machines you run on, you scale up the learning rate linearly. And this kind of assumes that you're using a mean reduction loss, which is like the default for pretty much every loss. And the NVIDIA paper for scaling up batch size to 32K basically had the same practice of learning rate warm-up, but introduced a new optimizer. We're in the process of testing out this optimizer, and potentially we'll introduce it to TensorFlow. So the last topic I'll go into are embeddings. So embeddings are, you might not already be aware of them. And I'll first mention that if you're not aware of them and you want to train machine learning models, you should probably be aware of them, because they're, with the exception of image models, they're used in pretty much every kind of production model. So if they're used in most models and you want to deploy them, then you should be aware of them. And like, I'll talk a little bit about how to make them work at scale. So as some background, what are embeddings? So there's like several ways of thinking of it. You can think of it as like essentially the equivalent of a hash table lookup into a vector of numbers. The way I think of it is like you have a sparse one-hot encoding of a tensor, and then you want to do a sparse matrix multiply to get the this embedding tensor out. So what do these numbers actually represent? So some people have kind of phrased them as thought vectors. So they kind of like represent a concept. So if you fed in here, like say a word like the word go, then this would be this like kind of a vector of numbers that represents the concept of go. And you can actually visualize what neural nets learn when you actually create embeddings. So this is just the toy MNIST data set, but you can, this is TensorBoard, so that comes with TensorFlow. So you can actually use this for tons of different tasks. And people have actually used this to visualize what essentially words look like. But you can see like the distance between different numbers in this space. And if you were to apply it to words, you could also see what words are actually nearby other words in this embedding space. And this basically like projects the original embedding vector of however many dimensions, like 100 dimensions, down into like a 3-dimensional visualization. And we actually published the model that we're using for Google Play. And just as a note here of like how this works concretely is typically you'll have something like demographics, apps, and you'll do a lookup into the embedding table, and you'll essentially concatenate this and feed it into a dense neural net. This type of model structure is actually generally pretty common. So we made this and open source this framework called Wide and Deep that allows you to do this and create and train such models pretty easily. So why do embedding tables matter for scale? These can actually end up being pretty large. So these embedding tables, like as a simple example, like suppose you want an entry in the embedding table for every bigram, which is a combination of two words that you see together. Then the number of entries would be like the number of words squared. And then you would then multiply that by the size of the embedding, which might be like 100 times the size of a float. So for each of these, it would be like 400 bytes. So the best practices are for distributed training. You typically want to shard these embedding tables. TensorFlow supplies a way for partitioning variables. you can shard these across multiple parameter servers. For smaller embeddings, you can actually do the embedding lookups on GPU, but for larger ones, you typically want to do them on CPU and then feed the embeddings directly into your GPU. There's something called out of vocab. So you can build up a vocabulary of things that occur commonly that should appear in your embedding table, and then you can essentially do a hash to kind of mix the items that occur pretty rarely. For some final thoughts, I kind of talked a lot about scaling distributed training today, but I'll mention that before you should scale training, you should actually scale your data. So a lot of these, like if your data set size is small enough, then a lot of times like traditional machine learning techniques will actually work better than neural nets. But the point at which this matters is when you get a lot of data. So there's a lot of ways to acquire more training data. You can scrape the web, or a lot of people are using Mechanical Turk. And another thing I'll mention is that unsupervised learning, which is learning without a label, is very hard to get right. So it's much better just to invest in labeling your data than trying to get unsupervised learning to work. And that's it. Any questions?
Earlier, you had a comment when you were talking about the neural translation model that you could only train on 1/6 of the data. I was wondering if you could talk about what the bottleneck was in that case.
I think it was just, I actually don't know specifically, but my guess is that it was the step time and making it work on like enough GPUs. So I kind of mentioned before that scaling actually just doesn't arbitrarily work. So you can't just like add GPUs and train faster. There's some point at which, at least according to current research, it just stops working and doesn't converge anymore. So you're limited then by the number of GPUs that can actually work, which probably is like in the 50-ish range or something. Yeah. So you're limited by computational power slash scaling concerns.
So I was wondering, you mentioned that you guys are learning the architectures of different networks, and you showed an example of an LSTM unit that for which you'd learn the internals. Have you guys tried to interpret what's going on inside those units?
I believe like people have looked at them for a while, and I don't know that there's any good interpretation of them. And the more recent paper from last month, which actually has been doing the same type of thing for image models, like essentially creating convolution cells, also creates like a somewhat complex to interpret unit, which I actually sat down to try to interpret and could not.
So I had a question about the interconnect stuff that you talked about. There was one slide where you showed different types of interconnects, some of them contributed by other companies, and one of them was called InfiniBand. And there was another statement that you made later on, like about how TensorFlow doesn't distinguish between 8 GPUs and one host versus 8 GPUs and 8 hosts. So doesn't that matter? Like, I mean, I thought like in practice, because the network is much slower than like say PCIe, so shouldn't TensorFlow abstract it all, or do I have to now start worrying about the fact that TensorFlow doesn't know that? Like,
yeah.
how does that work?
So in theory, that kind of matters, and it matters. I'll kind of go back to model parallelism. So it matters more for the model parallelism setting, where each device actually needs to frequently communicate with other ones. It actually matters significantly less for the data parallel case, because essentially each worker is like a step time for an image model might be like half a second, and this gradient reduction essentially. Say your model has like 20 million parameters, so this is like 100 megabytes. Sending 100 megabytes, each worker like sending 100 megabytes in a ring like this, that takes almost no time relative to that. So it really kind of depends on the task you're doing. And for data parallelism, this communication overhead in all of those settings actually usually doesn't matter as much.
And does TensorFlow, for the model parallelism side, like does TensorFlow help, or like that's something that we need to like be very wary about, like our hardware architecture?
Yeah, it's something you need to know, except if, so there's this reinforcement. I believe we've open sourced this, but if you have the compute to be able to test this stuff out, this would actually be communication aware. So like if there's a communication overhead here, and you need to do device assignments based on that communication overhead, then this would be aware of that and then can actually do placements based on that fact. Yeah.
How much of a delta is there between the performance with synchronous SGD and asynchronous SGD? And if there isn't one, like, why do you think that is?
So it's like you can measure performance different ways. And like say you have an image classification model, you can measure performance as like images processed per second, or you can measure as time to convergence. And what the performance that people actually care about is time to convergence. The performance number that people actually print usually is images per second in benchmarks. And generally speaking, I believe like if you have a setup where each machine is roughly equivalent, then in synchronous settings, like time to convergence usually is better.
For the TPU v2, I think there are 228 by 200 by 128 by 128 matrix multiply units. But in v1, there was like a single 256 by 256. It might have been like lower precision though. Can you comment on the architectural differences? Like why move from 256 by 256 to 2?
Yeah, they're actually just very different like hardware. Let me see. I have to see what I can talk about. They're just generally very different hardware. So the first version of TPUs was actually built specifically to make inference fast. And this one is specifically built to make training fast. And I wasn't there at the time that they made these decisions. And yeah, there are probably things that could be done differently. But actually, like, I guess I wouldn't be able to speak to the specific differences in the matrix units. Yeah.
Is anybody still playing with different activation functions, and especially as it relates to the different quantization, like FP8 versus Int8 quantized versus FP16? Does that matter at all?
Yeah, so there's research going into it. For the most part, for most models, people settle on just straight rectified linear. But there's like a recently introduced one called Hseu, and that works well in very like specific cases. I don't know of any other stuff that's going on in this space. Yeah.
This is probably a little bit esoteric, but I want to get back to another point you made about so for asynchronous data parallel algorithms, so it's basically where you're doing kind of parameter server type type optimization. I think you had mentioned that kind of looks like it looks sort of similar to regularization in some ways because you're basically like there's some stale set of parameters that you're updating. Do you know of any work around kind of quantifying that at all, or is that something that can be made more theoretical?
So my understanding is actually asynchronous training usually results, this could be wrong, but my understanding is asynchronous training usually actually results in worse model quality than synchronous training. And the regularization effect of that actually tends to not matter. So there's actually this paper also at iClear 2017 that talked about like generalization for neural nets, and that it basically kind of spoke to that like for a lot of kinds of neural nets, regularization almost doesn't matter. For sufficiently large neural nets with sufficiently large data set sizes.
I had another question around dropout, and is there any way, or how are people doing in models where you have high dropout layers, can you do parallelism through picking different, basically, regions to train different connections on different nodes and training it?
Yeah, I'm not too familiar with work in that area, so I probably can't speak to that.
Sort of in the opposite direction, kind of popping up a few levels of the stack. What is so given that parallelizing and distributing work in machine learning seems to be kind of so crucial to getting this to work in real world domains. Like going forward, what is sort of like the most like personally exciting advances that you see kind of coming down on the horizon? Like, what are you most excited about, or what do you want to be working on, or what's going to be the most impactful for
Yeah, I think the two biggest things are the learn-to-learn stuff. Actually, there's just like tons of things you can apply that to. So anything where you can develop a search space and choose a reward, you can essentially like test out different kinds of things for. And yeah, I guess I can't talk about other things we're testing out, but you can imagine that we're all trying to learn other things. And the second thing is, a lot of the most exciting things that I mentioned here are actually just like reinforcement learning related. And I think there's just a lot of stuff in reinforcement learning that just has like great applicability, but is just undiscovered.
So yeah, I guess more on sort of the learning to learn. You discussed a couple of different results from that seem to transfer like very well between different problems. Is there any sort of rule of thumb or intuition behind sort of what learning to learn type results do transfer well between multiple problems, and which types of thing you should really just be redoing for every sort of new problem that you want to apply it to?
Yeah, I think the ones that people tested out that worked well for other problems were mostly people kind of looked at them and like thought, does this look simple enough, or does this kind of make sense? Although I guess it doesn't apply to the RNN cell that it developed. Yeah. Sorry, what was the second part of your question?
I mean, I guess I'm just trying to figure out, like, if I'm trying to decide, like, okay, is it worth it to run this learning to learn experiment? Is there a way to think about, like, okay, like, this aspect of the problem, like, I should expect, like, if I have a new problem, I should try to run, learning to learn on this element of the problem, whether it's the model design or the placement, or, the RNN cell design or whatever, versus like, okay, well, somebody's done the experiment once, they found a good result, and this is probably just going to transfer from problem to problem.
Yeah. So I think any problem domain where you've seen like significant improvements over the years through like research, can like where people are just essentially just iterating on different like types of models, that's something that a computer should essentially be able to do. Like, yeah, and I think more specifically, like when thinking about applying it to a particular problem, it needs a concrete search space, and then it needs like a small enough data set that you can like test out different like types of models or different designs on that search space.